Hello students, welcome to Educate. In the last class, we have discussed till 2.9. We have discussed the questions till 2.9 of the chapters Atomic Structure. Now we will discuss from 2.10. Question is here, electromagnetic radiation of wavelength this one is just sufficient to ionize sodium atom. So sodium atom, what happened here? Suppose this one here, sodium atom, here is sodium atom in this case, and from here a photon is striking, their wavelength is 242 nanometer, this one, and it get ionized, means it just released from the atom. So it's asking the ionization energy of sodium. So what is ionization energy? Ionization energy is the minimum amount of energy which must be supplied to the isolated gaseous atom. The minimum amount of energy which must be supplied to the isolated gaseous atom. The minimum amount of energy required to release an electron from an isolated gaseous atom, that is ionization energy. So when a photon is striking here, then how much energy has been provided so that the electron has been released from there, that you will have to calculate. So obviously how much energy has been supplied? So energy has been here supplied in the form of electromagnetic radiation. How much energy is supplied? So E equal to hc upon lambda here, because wavelength has been provided. So that's we can calculate E equal to hc upon lambda. Lambda is 242 nanometer. That you have to calculate. So how? 6.6 into 3 equal to how much? That divided by 242. So 0.081, that is 0.081 into 10 to the power here how much? 9 go there, so 9 and 8, 17, so 17 here 10 to the power minus 17, that much joule. So in case of that is that much joule. So to calculate, so in case of kilojoule, that will be equal to 0.081 into 10 to the power minus 17, that into 10 to the power 3, that much kilojoule. So that is here 17 minus 3, 14, 0.081 into 10 power minus 14, that much kilojoule, that will equal to 8.1 into 10 power minus 12 joule. So that is, so ionization energy of the sodium atom will be 8.1 into 10 to the power minus 12 joule. Okay. Now that was the question 2.10. Now 2.11. Let's see. What the question here is, the power of the bulb has been given, that is 25 watt. That emits monochromatic yellow light of wavelength has been given there. So the wavelength of the yellow light has been provided, and it's asking rate of emission of quanta per second. That is, power of the bulb is 25 watt. That means in 1 second the bulb emits the energy of 25 joule in 1 second. Power of the bulb is 25 watt, means the bulb emits 25 joule of energy in 1 second. That is, now wavelength of the light has been also given. Wavelength has been given. So energy of one photon you can find out by that. Okay. So from the bulb, the energy emitted in the form of radiation only. So photons releases from the bulb, and in 1 second total energy released is of 25 joule. The wavelength of photon has been given, so you can find out the energy of one photon. So total number of photon will be total energy emitted divided by the energy of one photon. Simple here. So let's see. Firstly, I make it short. (25 joule this one. So energy of one photon wavelength has been given how much? 0.57 micrometer. That means 0.57 into 10 power 6 meter. Micro means 10 to the power minus 6. Or it will become 40. So 6.6 into 3. So how much is there? And it will be here how much? Meter cancel out, second cancel out. That will be in joule. So now you will have to divide 19.8 by 0.57. So 34.73. That is okay. Very easy question that was, because main here concept was that the power of the bulb is 25 watt, means the bulb emits 25 joule of energy in 1 second. And since all the energy released by the bulb are in the form of electromagnetic radiation, that means photons emit from the bulb, and as a result 35 joule of energy emitted by the bulb. 35 25, sorry, not 20, 35, 25. So as a result 25 joule of energy released by the bulb. So number of photon was asking. So total energy released by the photon, that means a number of photon emits from there. In that case 25 joule of energy releases. So that is here. So energy of one photon I have calculated, and then divide the 25 joule by the this number of energy of one photon. So we can get, in this case, in this manner we can get the number of photon emitted by the bulb in 1 second. Next question. In this case here, question is asking, the question is the electrons are emitted with zero velocity. This question. Yeah, electrons are emitted with zero velocity. Velocity is zero. That means just electron has been only released from the metal surface. So electrons are emitted with zero velocity from a metal surface when it is exposed to radiation of wavelength this one. So energy of one photon, that means what is the energy of this photon? That is just sufficient to release the electron. So it's asking threshold frequency and work function. So this energy, firstly, when we will calculate the energy of photon, that energy will be equal to work function, because that energy is only sufficient to release the electron, and there is no kinetic energy. Kinetic energy here zero, because velocity of that electron is zero, so there is no kinetic energy in that case. So the energy of photon will be equal to the work function, and that was here. So frequency also we can calculate. Okay, so to calculate the frequency, directly going on the energy not required. Since here the wavelength is given, so frequency directly, that is, so this one is maximum wavelength or is threshold wavelength. So let's see here. So as you know, C equal to nu lambda. So threshold frequency will be how much? So this is threshold wavelength, this is threshold frequency. So 3 into 10 power 8 meter per second, that upon this 6800 into 10 power minus 10, that much meter, that will equal to threshold frequency nu naught. So we can write here this one, nu naught will be, that much it is threshold frequency, that is velocity of light upon wavelength of light. So here it is 18, so 3 into 10 power 18, that upon 6800, that is meter will cancel out here, second inverse, so that will be equal to the threshold frequency for the photoelectric effect. So this is here how much, how to calculate. So 3 divided by 6800. So 0.00044. That into 10 power here how much? That is 18. So 10 power minus 18. That is equal to threshold frequency. So threshold, that is here 1, 2, 3, 4. So 4.4 into 10 power minus 14. Second inverse, or 4.4 or 4.4 into 10 power minus 14 hertz. That is the threshold frequency. Okay. Work function E equal to SC upon lambda. Work function E equal to, you know already, SC upon lambda, or you can also find out here threshold frequency you have calculated, so that you can also do H nu, whatever you would like. In that manner you could find out the work function. Work function is equal to the energy of photon striking to the metal surface, and that is equal to H nu or SC upon lambda. So here, so directly you can put here. So second inverse will cancel out, 6.6 into 4.4. So that is here, work function is that much. Okay guys, now let's see next question. Question is, what is the wavelength of light emitted when the electron in a hydrogen atom undergoes transition from an energy level with n equal to 4 to an energy level with n equal to 2. That is, electron is emitting from n equal to 4 to n equal to 2. Then what is, how much energy will emitted? So energy emitted when electron, when in this case we will how to solve, when electron will be in n equal to 4, then what will be their energy? And then after we will calculate when electron will be in n equal to 2, that means in second cell, then what will be their energy? Difference of that energy will release in the form of electromagnetic radiation. So that will be here. So wavelength, so energy decrease in when electron will revolve in n equal to 4, that means when electron will revolve in fourth cell, then what is their energy? And then after we will calculate when electron will be in second cell, then what will be their energy? Difference of that energy will be equal to the energy of photon released during that process. So let's see. So electron is when it is in present in fourth cell, so that is equal to, you know already, that is the value. So that is here, joule per atom there is. So that means for one atom only I am calculating. So this one energy joule for one atom, this much joule energy release, that equal to same one electron will be present in second cell, their energy will be so difference in energy, that will be equal to E2 minus E1. That means that much energy will release, that much. So energy released by the electron will be energy, this is minus sign, that means that much energy will release by the atom when electron will fall from n equal to 4 to n equal to 2. So this one is when electron will fall from n equal to 4 to n equal to 2. So that is, and what the question, the one of the question is, you have to find out wavelength. So that is energy released by this one. So that means radiation, energy of photon will be also that much. How much energy released by the electron? So electron releases the energy in the form of electromagnetic radiation. So we will write energy of and you also know E equal to Hc upon lambda, energy of photon that equal to Hc upon lambda. So energy Hc upon lambda, energy of photon is that much 1.52 into 10 minus 18 joule. So that will equal to H 6.6 into 10 minus 34 joule into second. Velocity of light 3 into 10 power 8 meter per second. That upon lambda. So lambda will be equal to goes this side. So this side comes, energy will come this side. So lambda will be equal to so what is here? Second and second inverse will cancel out. Joule and joule will cancel out. So only that left meter. So now here calculate 6.6 into 3. So 6.6. So firstly 6.6 into 3 equal to what? That divided by 1.52. 13.02. So that will be 13.02 into 10 by here 18 will go above, so that will come positive, so that will be 26. So 34 minus 26 8, so that will be 10 to the power minus 8, that much joule. So that will equal to 1.302 into 10 to the power minus 9 joule. This is 10 to the power minus 9 here meter, sorry here not joule, meter. So here that much meter, and the unit of wavelength is meter. SI unit will be meter. So that is. So in this case, this question was solved in this manner. That is here, since that much electron when fall from n equal to 4 to n equal to 2, so energy of electron was decreased. So energy of electron was decreased. So the rest amount of energy will emit in the form of electromagnetic radiation. So decrease in energy of electron will be equal to energy of radiation or the energy of photon emitted by the atom. So energy of photon, that's calculated here, and also we know the energy of photon, that is equal to Hc upon lambda. So during that course, the wavelength of the radiated photon could be calculated. Okay guys, now let's see another question. Listen guys, this question is conceptual. You have to think. Listen. First of all, let's see. Watch out. Read the question firstly. This one. Question is here. The electron is revolving in the fifth shell of the hydrogen atom. In hydrogen atom, electron is revolving in fifth orbit, and it is asking that how much energy required to ionize hydrogen atom. So hydrogen atom how to require? So that is here that electron when goes on the infinity, when electron will go in the infinity, that case the energy of electron will become 0. So how much energy this hydrogen atom will gain to jump, how much hydrogen energy the electron will, this hydrogen atom will gain, so that the electron present in the fifth shell will jump into the infinite cell. That means that the electron will go outside the influence of the hydrogen atom. In that case, how much energy required? So when electron present in n equal to 5, that we will calculate, and when electron will be at infinity, so that will be 0. So difference of energy will be 0 minus how much the energy of electron in this case, that will be the ionization energy, or that will be the energy of electron, energy required to ionize hydrogen atom. And how to then after you will have to calculate the ionization enthalpy of hydrogen. So how we will find the ionization enthalpy of hydrogen? So when hydrogen electron will revolve in first cell, then what will be their energy? That so, and when electron will jump into the infinite cell, n equal to infinity, then 0. So that means here we will compare the ionization enthalpy as the energy of electron when it will be present in first cell. Okay, I am solving here also. Let's see. That is energy of electron at infinity. So that will equal to 0. So energy required. That's why ionization enthalpy will be equal to energy at infinity minus energy at fifth cell. That will equal to 0 minus that is, so therefore ionization enthalpy will be equal to 8.72 into 10 power minus 20 joule. Ionization enthalpy not, that will be this one is energy required to ionize. So it will be energy required to ionize. This one is, so it will be, so energy required to ionize the hydrogen when the electron present in fifth cell jumps into infinity. So to loosen the electron, when electron will lost by the hydrogen atom, that will go at the infinity where the energy of electron will be 0. Now compare with ionization enthalpy. So for ionization enthalpy, in case of ionization enthalpy, electron present in first cell will jump at the infinity. So at infinity, energy of electron will be 0, and in first cell we will have to calculate. So in first cell, the energy of electron will be minus 2.18 into 10 power minus 18 joule. So let's see here. So that means energy, ionization enthalpy of hydrogen will be that will be equal to energy at infinity minus energy in first cell. That will equal to 0 minus 2.18 into 10 power minus 18, that is joule upon 1 square. 1 square, that will equal to 1 only. So that will be equal to 2.18 into 10 power minus 18 joule. You will have to compare. So energy, you have to compare this energy with this energy. So energy when electron is in fifth cell, that upon ionization enthalpy when we will calculate. So that will equal to energy this one, that one upon energy here 2.18 not minus plus here 2.18 into 10 power minus 18. So here will be 10 power minus 2 and 8.72 divided by 8.72 divided by 2.18, it will be 4. So that will be 4. So 4 into, that means that will equal to 4 into 10 power minus 2. So that is 0.004 times. Okay. So ionization enthalpy, this one is, or ionization enthalpy upon E5, that we can also find out. This one. Okay guys. So what we did, when electron was present in fifth cell, then their energy will be what? That we have calculated. Then after, we assume that since ionization, it is here, how much energy will require to release the electron here. So n equal to infinity. So n equal to infinity, the energy of electron was 0. So to this case, the energy required to release the electron, that will be equal to n equal to 0 minus energy in fifth cell. 0 minus energy of electron in the fifth cell. Now, when we will have to find out the ionization enthalpy. So, in case of ionization enthalpy, naturally the electron of hydrogen revolves in the first cell. So, equal to 1, that will equal to energy of electron when it will be in first cell will be minus 2.18 into 10 power minus 18 joule. So, in first cell, the energy of electron is minus 2.18 into 10 power minus 18 joule, and in n equal to infinity, that will be 0. So, energy required to release the electron from n equal to 1 to n equal to infinity will be 2.18 into 10 power minus 18 joule. So, we have compared the how much energy will require when electron jumps from n equal to 5 to n equal to infinity with respect to when electron is in first cell and it jumps into infinity. So that comes 4 into 10 power minus 2 and joule will cancel out. So that means that much times. So we can say that E5 will be equal to 4 into 10 power minus 2 times of ionization enthalpy of hydrogen. Okay. Now let's see other question. What is the maximum number of Mason lines when the excited electron of a hydrogen atom in n equal to 6 drops to the ground state? Okay, here n equal to 6 to here I am showing you in detail. You can also find out in the exam for the NEET examination and CUT examination. You could also develop a trick if you will watch out how this is done. So let's see. Electron is present in 6th cell and that falls to the ground state. So how much transition is there? So what's the simple here? How much simple it is? So n equal to here 1, n equal to 2, So electron can jump from n equal to 6 to n equal to 5, n equal to 6 to n equal to 5. Same electron can jump from n equal to 6 to n equal to 4, n equal to 6 to n equal to 3, n equal to 6 to n equal to 2, n equal to 6 to n equal to 1. How much? 1, 2, 3, 4, 5. Okay, so simple trick is there. From 6 to 1 it will go. So how much lines it will pass? 5 lines. So there is 5 lines between 6 and 1. So there is 5 lines between, from, because 6 and 1, that we will have to also consider. Between 6 and 5 there is 4 lines, but electron will have to fall from n equal to 6 to n equal to 1 also. So that's why there will be 5 lines. When electron will fall from n equal to 6 to n equal to 1, there will be 5 lines. Okay, so that is here. So there will be 5 emission lines when the excited electrons of a hydrogen atom drop in from n equal to 6 to the ground state. Now let's see 2.16 question. First part. Question is, in the ground state or in the first state, first orbit of hydrogen, the energy associated is minus 2.18 into 10 to the power minus 18 joule. So what is energy associated with the fifth orbit? Very easily you can find out. So equal to, that's just I am reminding here. So equal to here of this one, energy of electron, that equal to minus 2.18 into 10 minus 18, that upon n square, that much joule. And already n equal to 5, you will have to find out. When n equal to 1 you have put it, that will be minus 2.18 into 10 minus 18, that's why. And n equal to 5, because that's we have already this type of questions we have solved. We have utilized this concept. So as we have utilized these concepts, so could not you solve this question by yourself? Okay, so this apply this formula, do the question. Next question. Here, calculate the radius of Bohr's fifth orbit of the hydrogen atom. So you know already Rn is equal to R naught into n square. By this formula, apply this one, you could solve this question very easily. N equal to here 5. And in cell number, so n equal to 5, put that. You can find out this question very easily. Now let's see next question. Calculate the wave number of the longest wavelength transition in the Balmer series of hydrogen atom. Okay guys, Lyman series, when electron falls from any cell to first ground state, that is n equal to 1. When electron will fall from n equal to, okay, just goes on the this one hydrogen spectrum also. As you have seen here, hydrogen atom spectrum we have discussed already. So in Lyman series, you comes in the conclusion that in Lyman series, the electron falls from n equal to, from any cell to n equal to 1. Then that was the Lyman series. And in Balmer series, from any energy level, electron falls to n equal to 2. So let's see here, same. This was Lyman series. Oh, here not written. Okay. It is Lyman series. Here, Balmer series, Pascal series, Beckett series, Fund series, and here written already. Balmer series. Visible light falls under the Balmer series. Okay. So question was, let's see. Calculate the wavelength, number of. This question we did. So this one is longest wavelength transcend the Balmer series. Longest wavelength means their energy will be least, and Balmer series n equal to 2. That means electron falls to n equal to 2. So least energy released by the electron will least energy released will be from when electron falls from n equal to 3 to n equal to 2. So that will have when electron will fall from n equal to 3 to n equal to 2. In that case, the energy of the photon released will be minimum and wavelength will be maximum. So let's see here what is that. So wave number that will you have to find out. So energy of electron when that falls from n equal to 3 to n equal to 2, that will be, so that will be equal to how much? Minus 2.18 into 10 minus 18 upon n equal to 3. So okay, to n equal to 4. So that is 9 minus, okay, directly to take. Why this one plus here? Let's see why here plus, because that will be minus and this one is minus. That's why plus. Okay. This is change in energy of electron. Okay, this one is change in energy of electron. So energy of photon will be in positive sign. That much joule is here. So that means energy decrease in energy of photon. That means energy of photon change in energy of this one. So therefore that will be equal to how much? That will be here same, negative sign will be ignored. So 3.02 into 10 power here writing so multiplies 10 power minus 17 joule. 3.02 into 10 power minus 17 joule. That is the energy of radiation. And you have to find out this question we are discussing. Wave number. So wavelength you know already, E equal to Sc upon lambda. So E equal to Sc upon lambda you already know. So from there we will find out. So energy of photon is that much. So wavelength of photon you already know, E equal to Sc upon lambda. So lambda equal to Sc upon E, that is that much meter. Lambda will be equal to that much meter. And you have to find out wave number. That means 1 by lambda. So 1 by lambda. So this will go, that is which is in the denominator. That will come in the numerator, and which is in the numerator. That will come in the denominator. So that will be equal to minus 30, it will go above, so that will become here 10 raised power here how much, 17 plus 34 minus 8. Sorry guys, here is minus 17. Here minus 17. So minus 17 plus 34 minus 8. That will be, so minus 17 and minus 8 minus 25. So 34 minus 25. That means 9. So 10 power minus 9 will be there. 10 power, no, plus 9. 10 power 9. So now 3.02 divided by 6.6. Zero 0.15. So wave number will be that much. It is in meter, so meter inverse. So wave number of wave number will be 1.5 into 10 power 18 per meter. Okay, that was question number. Which question we are discussing? 2.17 that was. Let's see next question. Watch out this question. So here electron will have to shift from first Bohr orbit to the fifth Bohr orbit. And what will be the wavelength of light when emitted when electron will return back? Okay, so that is asking what this question. Demand of the question is when electron is in first Bohr orbit, and when electron will shift to fifth Bohr orbit, then how much energy will require? And when that electron will again fall from fifth Bohr orbit to the first Bohr orbit, then what will the wavelength of radiation? That is asking. Okay, in ground state that is also given, that much ergs. So in n equal to 5, that upon 5 square. In n equal to 1, energy of electron will be that much ergs. In joule, that has been, you already know the relationship between joule and the erg. Erg, the CGS unit. Let's see here how to solve. So energy in first cell already given. Energy of electron in the first cell already given here. So E1, energy of electron in the first cell is here minus 2.18 into 10 power minus 11 erg. So energy when electron will be in n equal to 5, their energy will be 5 square, that much ergs. So that will be equal to how much? Calculate the 5 square. The 5 square will be 25. Already it's understood. So that will be 2.18 divide by 25. First do that. So 0.0872. 0.0872. Guys, here not 11 or in arcs, that will be 11. So 0. This one into 10 to the power minus 11 arcs. So that here to side this side, that will multiply, so divide also. So 8.72 into 10 to the power minus 13. This much arcs. Okay, how much energy will be there? So energy here, energy has increased here. So that much energy will have to supply. So energy supply to the atom, that will equal to basic difference you find out. So 11 here, so you make into 10 power 13, so 872. No, that will be 0.00872 into 10 power minus 11 arcs. No, 0.0872. So nearly about 7.18 into minus 7.09. So that is 7.09 into 10 to the power minus 11 arcs. That is energy. So that much energy should be supplied to the atom, so that the electron present in first cell. So that much energy will have to supply to the atom, so that the electron present in first cell will jump into the fifth cell. And when electron will fall from n equal to 5 to n equal to 1, so that much energy will also release. Okay, so that means energy supplied to the atom will be that much, and energy released will be also equal to that much when electron will fall from n equal to 5 to n equal to 1. So that is here when That is, and what will be their wavelength? So energy of photon you already know, equal to hc upon lambda. So E equal to hc upon lambda. So lambda will be equal to hc upon E. H you know already, 6.6 into 10 minus 34 joule second into that upon energy is 7.09 into 10 minus 11 ergs. That will be here. Oh, sorry, here not joule second, here you have to convert here in case of ergs per second. Okay, so by that you have to you have to take care that the value of H you will have to convert it to ergs per second. Okay, and the relationship between joule and ergs you already know. So that's in this way this question could be solved very easily. Okay, so that was the question till 2.18, and from the question number 2.19 we will discuss in the next class. So it's all for this class. Thank you, Team Educate.